This video is about the solubility product constant, otherwise known as KSP. Yes, it's another K. Exactly the same as all the other Ks. Let's think about something that doesn't dissolve very well, like barium sulfate. This is a beaker of water. Here's the barium sulfate that's undissolved sitting on the bottom of the beaker. And then I've got some little bit that has actually dissolved. So in the water, I've got some Ba2 plus ions, I've got some SO4 2 minus ions, but I've got a great deal more that's a solid just sitting there on the bottom of the beaker. The equilibrium we can think about is some of the solid substance sitting on the bottom, and then some of it goes out into solution, some of this comes back and becomes a solid. That's the equilibrium that we're talking here, between the ions going down into the precipitate and some of the precipitate going out into solution. So we've got BaSO4 solid in equilibrium with Ba2 plus SO4 2 minus, and those guys are, of course, aqueous. Always think of it this way: the solid as the reactant, the ions as the product. Now, if you remember about K, solids don't go into the K equation, so KSP is only equal to Ba2 plus times SO4 2 minus. And then you just do all your normal ordinary ice boxes and everything exactly the same way we've been doing it. Where this gets a little complicated is when there are subscripts to worry about. So if I have something like BaCl2, that one would be in equilibrium with Ba2 plus 2Cl minus. And when I do my ice box, we don't care about these guys, but remember, this guy is X, this guy is 2X. We're so used to, in the acid and base, having everything be 1-to-1, that you have to remember this isn't 1-to-1 anymore. So the KSP, remember, is Ba2 plus times the concentration of Cl minus squared. And take a look, when you start plugging this in, presumably you have a value for KSP, you want to plug in to solve for X, it's going to be X times 2X, the quantity squared. So you'll notice that 2 is in two places. When you start trying to get this solved, it's X times 4X squared and 4X cubed equals KSP. So you're going to have to divide both sides by 4 and take a cube root when you want to find out what X is. Now X obviously isn't going to be pH or anything like that. In these cases, X is going to be the molar solubility. That is, X is how much of the Ba2 plus, in this case, dissolves in water, and how much the Cl minus dissolves in water is 2X. So that's what you're figuring out. You're figuring out how much is actually dissolved in water. Now, when you're thinking about dissolving, there are some things that will change the solubility, and mostly they're applications of Le Chatelier. So, for example, let's say I have CaF2, and I want to calculate its solubility, but in a solution of 0.010 molar NaF. Oh look, common ion effect. There's F minus already in solution. That's going to affect our solubility. This is the same way you did common ion effect back at the beginning of this chapter. We don't care about how much of that initially we have, but we do have some of that. So when we do our icebox, that's minus x, that's plus x, sorry, and that's plus x. This is x, this is 0.010 plus x. Should be beginning to look familiar to you. The KSP, which in this case is 3.9 times 10 to the negative 11, is going to be x times 0.010 plus x. And if you solved that, you would find x equals 3.1 times 10 to the negative fifth. This number here is, of course, smaller than what it would be if I had put the CaF2 in pure water. So that's that whole common ion effect. Now, sometimes they're sneaky about this. It's not that they say CaF2 is in a solution with some extra F minus. They actually say it's in a solution with something that's going to react with one of these guys. So maybe you have CaF2 in an acid solution. Well, now if you think about that, in an acid solution, I've got lots of extra H pluses lying around. H pluses will react with F minuses to make HF. That's going to be Le Chatelier in the other direction. It's going to increase my solubility because some of the product is getting taken away. Some of this F minus is going away because it's reacting, and that shifts things this way. So that's something to worry about when you're talking about a KSP problem, is do you have any kind of Le Chatelier effect? Lots of times it's an acid solution or basic solution, and you have to worry about what effect the H pluses and the OH minuses have on the equilibrium.